get their popcorn ready. So let's see, what's our actual time in here? Just, oh, we're a half hour late. Oh, I'm sad. Okay. You know, give me just 1 second. To be careful, I want to measure the potential between my camera here and the frame of the monitor. And by potential, I mean voltage. It shouldn't be an issue, but I'm working off a 240 instead of 120 here, and things might not be isolated. I just want to make sure that if I accidentally touch my video camera, which I believe is grounded to the metal frame of the monitor, that it's not going to explode anything. It shouldn't. There's no reason for it to, but you know, it's better safe than sorry. So to do that, I'm just setting my meter on AC volts. And I'm just putting 1 meter lead, it doesn't matter which one, just somewhere on the frame, you know, just hanging it on the frame like that. And then using the other meter lead, I'm checking the ground of my computer and like that. I just want to make sure, yeah, see, there's no potential there. Make sure the camera, it's metal on the camera. I'm just making sure I really touch ground. Yeah, so there's no potential there, so that's good. Okay, so the day has finally arrived, yay! The day we've been leading up to. The reason that most of you are here, right, is CRT monitor repair. So we're going to spend the next 2 days on this. It does take me all day today to go through the theory of operation and start looking at the circuits. As I promised you that every day is going to get a little more complicated. If yesterday might have blown your mind a little bit at the end when we started talking about a more sophisticated voltage regulator circuit in the linear power supply, or the crazy way that a switched mode power supply operates, today's going to be more so. This morning I'm going to go over, oh, bless you, gesundheit, salud, as we say. Sorry, so see what you've done to me, Annick. Anyway, so this morning, I really need you to relax. Relax. This morning, not hardcore. I'm just going to tell you how monitors work. You probably kind of already know, but specifically how it works and stuff like that. But this afternoon, we're going to start looking at the actual circuits themselves, and we're going to look at the schematics and see how they work. You have a nice schematics book, a beautiful book of schematics, and most of the schematics are there. And then tomorrow I'll have to finish up with probably a little bit of circuit description. I'm not sure if I'll be able to get it all in one day. Usually I can. But tomorrow is kind of a hands-on day. Tomorrow, the pace of tomorrow is much slower. Much slower. I really don't have a bunch of lecture planned for tomorrow. Other than Philippe and Annick, did anybody bring something to look at, to fix, or to troubleshoot? But Hassan, you have dead stuff here?
Yeah, we've got all these.
Oh, apparently, okay, all right.
Far from the people.
Anyway, so,
Excuse me.
yes, sir.
Just for
Yeah,
lunch,
yeah, sure.
is everybody okay with? I'm gonna go Dutch lunch. So we have some Dutch fried fish, and maybe people want to try the Dutch herring, so the raw fish. Okay.
Well, sushi I'm good with, but not herring.
No problem. We also have some sandwiches, but I'm gonna get some fried fish. Is everybody okay with that?
That's nice.
Yeah.
Lekker.
Yeah, lekker.
Is this the most used word in Dutch? Lekker. I see it everywhere, and it means like good or nice or tasty.
Yeah.
Lekker
Lekker.
or heerlijk.
No, but the word, specifically the word lecker, I see it everywhere. I just, you know, on TV, maybe it's just like one of the only Dutch words I recognize, and I go, oh, lekker. Every time they say it, I say it, oh, lekker.
This is lekker. What you're drinking now is lekker, bro.
Wow. See, everything is lekker. That's what I'm telling you.
The weather can be lekker too.
Yeah, right. Nice. Yeah, lekker. How's the weather? Oh, lekker. All right. So, as you probably know, so tomorrow we're just going to try to fix some stuff, make some voltage measurements, and kind of diagnose some stuff, play around, something like that. So, as you probably surmised, I like CRT monitors. I like working on monitors a lot. When I first started in this business, it was like back in 1971 or 72 or something like that. I had already been interested in electronics, and in a shop full of electromechanical pinball technicians, pinball mechanics really, I was the only guy that knew electronics. And so right away when Pong came out and we had to fix, what's that? Oh, it's a TV turned into a monitor. Well, you know, what fun is that? I was the only one that could fix them. So I was always the go-to monitor guy, and you know, I started with black and white monitors and worked my way up, but I like working on. Number one, it's really fascinating how they work. I just think it doesn't exactly blow my mind anymore, but it's just amazing to think about how monitors and television in general works. It just is. How the television itself, how the monitor itself works it's just fascinating. But the other reason is that once you've worked on monitors for a while, you see the same kind of failures over and over and over again. So it doesn't really take a genius to work on a monitor. Mostly it's experience. Oh, I've seen that before, it's this. Oh, a fuse is blown. Well, there's only two things that'll do that. You know, it's got to be this or whatever. So in general, when I was working for an operator and I had a bench full of bad monitors to fix, I could produce a bunch of monitors, and a lot of times it was just changing electrolytic capacitors toward the end of things. But in the beginning, it wasn't that. It was lots of other weird stuff as they learned how to build monitors, basically. So anyway, I love monitors. I like talking about them. I know that's why you're here. You have kind of an awesome responsibility now because you're trying to maintain sometimes monitors that are 40 years old. You know, there's monitors built in the 80s that your guys are still operating and are limping along, and you know, I don't know what's going to happen when we run out of CRTs. Right when, in the United States, right when LCD monitors first started coming out, people were setting perfectly good TVs on the side of the curb for garbage pickup. There was a little group of people in the United States, many groups really, that would swoop them up and I guess they had a place to store them. I don't know, a bunch of CRTs. So there's lots of CRTs out there that were for consumer TVs. But once those are used up, that'll be it. They haven't made CRTs in a long time. So anyway, I'm glad you're doing it. All right. So the monitors that we're working on, the monitors we're talking about here, are technically known as raster scan monitors, as you probably know, for reasons that we'll talk about as we go through the class. So I'd like to start out with taking a look at the picture tube itself. The picture tube itself, which is known as the cathode ray tube. The CRT stands for cathode ray tube, as you know. So let's take a look at the CRT itself. So here's the actual CRT itself. It's made out of glass, as you know. It has a nice thick front. It's not thick maybe for the reasons that you think. The front of the glass is not thick so that you don't break it, although it is nice that you won't be able to break it by hitting it. It's leaded glass. The glass itself is leaded glass. There's a lot of lead in the glass. If the glass didn't have lead in it, the monitor would emit X-rays, and that would be like a safety hazard. So like in California where I live, these are technically toxic waste because of the lead in them. and we actually have to take them to a special recycling company, and we have to pay to have them recycled. Normally when you recycle, you bring them stuff and they give you money, but you actually have to pay a company in California anyway to take care of this. We will see later on in the discussion where there's a certain failure that can happen in monitors to cause the X-ray production to increase a lot. And in that condition also the leaded glass protects you, and there's another circuit that protects you as well. We'll be talking about X-rays as we kind of go through this thing. So down here in the neck of the picture tube, there's something that's drawn on the schematic diagram like this, like three backward, no, I didn't make this big enough, like three backward L shapes, like that. And these are the cathodes, of the cathode ray tube, cathode. So there's three cathodes, there's one for each color, one for red, one for green, and one for blue. As you know, red, green, and blue are the three primary colors of light. By combining red, green, and blue in different combinations, we can make any color that we want. So I'm sure you're familiar with color bars. Let me just call these up here. Hang on a sec. Stand by. Shutterstock is unsafe? Come on, don't give me that. That's nuts. Oh, for goodness sake. Stop. Oh, for goodness sake. How many hoops do I have to go through? All right, I'll just stop here. I probably should have gone to Wikipedia. Anna, so you can't see this, can you?
Not really.
On the arcade machine, it has them built in as well.
Color bars? Oh, it does, doesn't it? That's
Yeah,
right.
well, they're RGB color bars instead of the.
Yeah, that's one. Oh, there we go. All right. Oh, but it doesn't have them mixed up, does it? Just RGB, right? Yeah. Well, Anik, just come up here for a second. I'm not sure. Wait a minute. I'm not sure how we're going to do this because you need to be able to see this board, the whole class. Yeah. Huh?
Yeah, there is an option for
If you click view and it's on left, there should be a full screen application.
full screen interface.
So,
Just right click the preview and then there's also.
oh yeah,
Oh, yeah.
exactly. You right click the.
Now we can see it anymore.
Now you can't see it anymore. Great.
You right click on the preview as well.
If you don't need the arcade machine,
I'm sorry. Say again, Chris.
we're not
full
using
screen
the arcade
projector.
machine, just move that out of it.
How's that?
Well, we will be though.
Oh,
I mean, for me, this is ideal.
If you move the table, you can put CFD back there. Computers away, table away, and then we can.
Okay, can we do that at this break? Just bear with me for just a
It's
second, right?
fixed. They can see it from the side on screen. So. On the monitor, this one.
Oh, okay. Well, we'll get it going anyway. These three guys are the cathodes. We are familiar with the term cathode, right? From the very first day, we saw the light-emitting diode had an anode and a cathode, and we looked at diodes, and diodes have an anode and a cathode. So this word actually means something. A cathode is something that emits electrons. Technically speaking, that's what a cathode really, really is on a real atomic level, I guess. A cathode is something that emits electrons. An anode is something that attracts electrons. Cathodes emit electrons, anodes attract electrons. So we have this gizmo known as the electron gun. Now, it's really called the electron gun assembly, really, because there are really these three electron guns in one. This is the electron gun assembly. So there's one cathode for each of the colors. One of them is red, one of them is green, one of them is blue. Red, green, and blue are the three primary colors of light. And by combining red, green, and blue in different combinations, we can make any color that we want. For example, if you combine, are you guys seeing this? Everybody can see it, right? If you combine red and blue, it makes this color known as magenta. If you combine blue here and green here, it makes this color, which is known as cyan, C-Y-A-N, C-Y-A-N, cyan. Cyan is a mixture of blue and green, and Pac-Man is yellow, right? Believe it or not, Pac-Man is made of a mixture of red and green. Now, I know that, like, if you're familiar with paints, mixing paints, it's like blue and yellow mixed together to make green or something, but paint is a subtractive process, and this is additive, and so red and green together make yellow. And of course, if all three colors are combined, the three primary colors, that's how we make white, and we make black by taking away all the colors, right? So we have this electron gun down here that contains these three cathodes. Well, on the schematic diagram, it's drawn like this kind of backward L-shaped sort of thing. But in the real world, what the cathode looks like is this. The cathode is like a cylinder like this. Coating the top of the cathode is an element known as barium, B-A-R-I-U-M. The object of the cathode is to emit these electrons. The electrons have to come from somewhere, and where they come from is a thin layer of barium that is coating the end of the little cylinder that is the cathode. Believe it or not, when you first get a brand new CRT, there is a finite number of electrons stored in it. This thing's an electron gun, and it's going to be shooting out electrons, and there's billions and zillions of them in there, but eventually that gets worn away. It gets used up. This is one of the things, the main thing that causes a picture tube to go out, to lose a color, or just be bad, just overall, is that imagine that this is a thin layer of barium, this element known as barium, on the surface. Over a period of time, it gets worn away. Typically, it gets worn away in the center a bit more than the edges. Over a period of years, and in our case, decades, right, that this CRT has been on, that barium layer gets smaller and smaller until eventually it gets used up. Once it's used up, that gun is dead. There's no way to fix it. The CRT is bad, and you're just done. But as I mentioned, it kind of does wear away from the center more than the edges. So what you typically end up doing is adjusting the brightness. As it wears out, you keep cranking up the brightness, and you end up with a really terrible image, because when something is dark on the screen, it uses the middle of this, and there's no barium left, and it's really super dark. But then when it hits a bright spot on the screen, it gets super bright because the bright uses the whole thing, and your contrast ratio goes way up, and it just looks awful. There's no way to fix it. I'm going to show you a very cheap, easy, free way to test your CRT to see if the gun is good or bad. You'll see how this works in just a second. It only takes a wire to do it like that, and we'll talk about that. So we have these three cathodes, and here they are. Let's see if I can get a nice good close-up of that thing.
Randy, what's the function of the rejuvenators?
Well, I'll get to that for sure. It's a good question. I will definitely cover it. So let me just make sure. Yeah, so you can easily see it here. This little cylinder that you see here is the actual cathode. If I turn this around, you can barely perceive it in between there. You can barely perceive the end of the cathode kind of sticking out, but not really very well. But there's three of the cathodes. There's one on that side, there's one on the opposite side, and then there's one in the middle, and they're red, green, and blue. So, you know, the green one is the one in the middle. Now, by itself, the barium doesn't really provide the electrons without a little help. As you know, inside the neck of the picture tube, there's a thingy glowing in there, and that thingy is called the CRT heater. It's called the CRT heater. And all it is a little 6.3 volt, like a light bulb, but it glows kind of orangey, yellow-orange kind of color temperature. It can work off of AC or DC. It doesn't matter whether it's AC or DC. Some monitors, it's AC. Some monitors, it's DC. Some monitors, that voltage comes from a winding on the flyback transformer. From a winding on the same high voltage transformer that makes the EHT, the high voltage for a monitor. There's another super low voltage winding on there that we will talk about in great detail that just makes a 6.3 volts. In other cases, they take it off of the switched mode power supply. In a monitor, it's very common to have a switched mode power supply, like we talked about yesterday, and one of the outputs is like a 7 volt output, and then they cut it down with a resistor to 6.3 volts, and it operates the heater. So the schematic symbol for the heater, the cathode is the backward L, the schematic symbol for the heater is like a little point, like this. That's the CRT heater, that little point. So sometimes they draw the CRT heater like that, and again, you just put 6.3 volts across it and it heats up. In some cases, they'll draw it like this, where they'll draw just one big heater like that, and then somehow they fit into 3 cathodes. I don't really know how they do it all the time, you know, something like that. So they are completely independent things, so this is really super important. Wake up, already wake up. I mean, every bit of today is kind of wake up, kind of. In the actual device itself, the heater goes up inside the cathode the little cylinder that is the cathode, but it cannot touch it. It cannot touch it. In the monitor, one side of the CRT heater circuit is grounded. One side is grounded. I'm going to show you later on in the class that when we ground a CRT cathode, it turns it on. If something happens and the heater droops or somehow touches the cathode, it will keep that gun turned on all the way. And you'll have a super bright green, red, or blue screen, like just a super, I'll demonstrate it for you later on, a super bright screen. So they are next to each other, but they are not touching each other. They're not hooked up in any way. They are 2 completely independent circuits. Let me see if I can show that to you. Ooh, getting cloudy. Let's see if we can. Well, I know what I'm looking for, but you may not. But the CRT heater is, there's a couple of little wires. Yeah, a couple of little wires here that go up inside the actual cathode here. So it's like there's 2 little wires here that go up inside, and that's the CRT heater. On the back of the neck board, usually it's silk screened. I don't think this one is. Let me cut the tie wraps off of this thing and just see if it's labeled or not. Hang on, stand by. Yeah, it's usually not. I mean, it usually is. In this case, it's not. Let me just try something here. Hang on a second. I'm not super familiar with this monitor. So on the back of the neck board of the monitor here, I'm sorry, on the back of the monitor is the neck board. Typically, the heater is pins 9 and 10. Typically, the heater is pins 9 and 10, and these are the two right at the top, right at the very top, right there. One of the pins is ground. This is, maybe it's not obvious to you, but it is ground. This big, large expanse is ground. And the other side should be around 6.3 volts. I just measured it with my meter, and it measures like 5.8 or something, and that doesn't surprise me. If the if the heater is driven off of high frequency AC, your meter is not going to respond properly. It's kind of an important thing to know. If you're measuring AC volts, your meter is really set to work off 50 hertz, 50 or 60 hertz. It's not going to read accurately at a higher frequency, which is what this probably is. But just let me show you that if I had a problem where the heater wasn't working, one of the first things I would do is measure the heater voltage right up here at the top between ground and pin 9. That's pin 9 and 10. The pins are numbered anti-clockwise. Clockwise around. Starting at the bottom, that's pin 1, and it kind of goes around like that. So I can measure that voltage. I'm just going to put my meter probes on pins 9 and 10. So I just have one pin on ground and one pin on pin 9. And oh, it is DC. Okay. So let's switch. I didn't get any reading on AC, so I switched my meter to read DC. And there's around 6 volts, 5.87. It doesn't bother me that it's a little low. We're going to talk about this later on. I'm going to show you a little trick for boosting up the heater voltage in case you need to increase it a little bit to kind of boost up the output of an old CRT. We'll talk about that later on. So that's kind of an important test. It's a test that I have to make periodically. When one of the first things people often do when they get to a monitor that's dead is, you know, peek in the back and look at the neck and see if it's glowing. And certainly if it's glowing, the monitor is turned on. And it's working, kind of. But just because it's not glowing doesn't mean the monitor's not on and you don't have high voltage and stuff like that. It's entirely possible that the heater circuit, which we will look at coming up in just a little bit, is open. That there's something wrong with the actual heater circuit, but the thing that makes the high voltage and stuff like that, that's still there. And so just because you don't see the glow, don't assume that nothing's on. It definitely can be on. Right. Anyway, so this is called the electron gun assembly, and as the name implies, it shoots out electrons. It's just like any other gun, except that the bullets are made of electrons instead of lead, I guess, whatever bullets are made out of. What I've shown you here is only part of it. This is just the cathodes. And when you heat the cathode, it releases a cloud of electrons. But it doesn't shoot them out. The cathodes themselves do not shoot the electrons out. They just allow the electrons to come out. In other words, it makes what we refer to as a space charge. That is to say, I've got this cathode here, I heat it up, and I've got this cloud of steam, only it's made out of electrons, but it's not shooting them out toward the front of the screen. That's the purpose of the rest of the electron gun assembly. The rest of the electron gun assembly consists of some metal bits which we refer to as grids. These are the grids. I'm so sorry, Anik, that you're not seeing this. We'll fix it at the door.
She can sit here.
Yeah, you can sit here. That would be a good thing. Okay. Well, then the heck with you. He's a nice guy. He won't bite you.
No food.
Your husband's in the room anyway. All right. So the rest of the electron assembly goes in front of the cathodes. In other words, the cathodes are here. Turn around. The cathodes I just showed you are here. They release the cloud of electrons, but there's a whole bunch of these what are called grids that pick up the electrons and do other things with them. Now, they're called the grids. They are not a grid like this. In English, a grid is that. But it's called a grid because the first vacuum tubes, valves for Chris, did indeed have elements inside that were grids like this. In a vacuum tube, there's a cathode that emits electrons. There's a grid that we can use to control the amount of electrons coming through. And then there's another element in a vacuum tube and a valve that's known as the plate. Well, we don't really use regular vacuum tubes or valves very much anymore, but this term grid has stuck with us. So it's not a grid in that it looks like that. It's just basically cylinders, not round cylinders, but just hollow cylinders that you hook up to the pins that come out the back of the picture tube. That's all it is. But here's the entire assembly. So in the entire assembly, you have the connector, of course, on the end, and you have the heaters, the cathodes, and then this one is really easy to visualize. You see these flat pieces of metal here, and you can see daylight through them, right there. So they're just flat pieces of metal, almost like a pie tin. With all of them have the 3 holes in them because we have to let the electrons out. I mean, every gun in the world pretty much has a hole in the end of the barrel to let the bullet out. So it's the same thing here, and there's the bullet where they come out. So there's a number of grids, and the grids are drawn as dashed lines. For example, there's grid number 1. It's called G1. We may or may not be discussing G1 very much. It really, as far as you're concerned and the way monitors work, we may or may not use G1 very much. G1 does have a name. It's called the control grid. It's called the control grid. Further up the line, there's another grid that's very important, and it's G2. G2 is your go-to grid. Excuse me. G2 is technically known as the screen grid. G2 is technically called the screen grid. And it's the grid that you are adjusting when you adjust the screen control on the back of a monitor. As you probably know, the super main brightness control in a monitor is called the screen control. Screen, S-C-R-E-E-N, screen control. So the screen control is the bottom control, and are you seeing this? Yeah. Sorry. It's the bottom control. The top ones are top one's focus, the bottom one's screen. And by adjusting the screen control, what you're really adjusting is the voltage on the screen grid in the electron gun assembly. So G2, the screen grid, is connected to the screen potentiometer. You had a couple of potentiometers in the kit that you built. I didn't specifically cover potentiometers in the class, but a potentiometer is just a variable resistor, right? So there's the screen grid, and that's, of course, attached to the high voltage unit, the flyback transformer. In UK, I guess elsewhere in Europe, they refer to this unit as the LOPT, line output transformer. That's a very bizarre name for that thing. We have an equally bizarre name. The official name for the high voltage unit, the flyback in a monitor, official name in the United States is Integrated High Voltage Transformer, or our IHVT, because it is a flyback transformer. We'll talk about all this later on coming up. It's a flyback transformer, but it is integrated with the diodes that turn it from AC into DC and the potentiometers for focus and screen and such like that. So we call it the IHVT. If you refer to that unit as the flyback transformer, or just plain flyback, everyone will know exactly what you're talking about. It's a perfectly okay term to use. So the screen grid, G2, is a fairly high voltage, and typically it can be adjusted for anything from maybe plus 130 volts DC to maybe, depending on the kind of monitor it is, up to 350 volts DC or something like that. This is important to know when we get into the real operation of the CRT coming up here. You'll need to know this, so I'll repeat it again. So depending on where you have the screen grid, you're either down at about 150 or 120 volts, or maybe up to 350. And of course, the higher the voltage, the brighter the screen is. And we'll talk more about that in just a second. In front of G2 is the focus grid. Focus grid. It's just called the focus grid. I don't think it has a number. It's just called the focus grid. And again, it's really just a tube. It's the big tube in the center. It's this guy right here, right in the middle. So we have like a couple of earlier grids, but there's one there, or there might be two. In a high resolution monitor, a more modern monitor, there are two focus controls. One controls the top and the bottom, one controls the left and right, or one controls the center, one controls the outside. It kind of depends on how they have the thing built. But the big tube is always the focus tube, the focus grid. And then in front of that is the grid that is known as the accelerator grid. Accelerator grid. And the accelerator grid is this one here, this outer ring thing here is the accelerator grid. And the accelerator grid is connected to this gizmo right here, which is known as the getter. So here's the accelerator grid. It's just this outer piece of metal here with the three holes in it. And connected to it is this piece of metal here, and this thing is known as the getter, G-E-T-T-E-R. Let's see if I can illuminate this a little bit. And if you look inside the getter there, do you see how it's has kind of a rough surface? It's kind of rough and gray kind of on the inside there, if you can perceive that. I think you probably can. Let me even get closer. Let's see. See how close I can get. There, you can clearly see it. See how it's all rough and funky inside there? So this is a very interesting thing. You don't really have to know about it, but I think it's fascinating, and I think the whole thing is fascinating, really. So this thing that you saw is called the getter. So the electron gun looks like this, and it has this pan thing here. It's called the getter. G-E-T-T-E-R. So as you know, a picture tube is a vacuum tube. It's a vacuum inside. If there were any air molecules inside, any molecules of any gas inside here, the picture, it wouldn't work. As the electron gun is shooting out electrons, it would hit this gas inside. So it is a vacuum inside. So they draw a hard vacuum as hard as they can. There's, as you know, a little nipple that's on the back of the the neck of the CRT. That's the thing you want to break off if you are going to discard a CRT and you don't want this high vacuum device floating around in the trash can. You just break off the nipple off the end and it won't implode or do anything weird like that. It just sucks the air in and away you go. But it's impossible for them to get all the oxygen out. It's impossible to get all the O2 out of the CRT. They draw as hard a vacuum as they can, but on Earth you can't draw a hard vacuum, so not really. So this getter thing is filled with flash powder. I think it's magnesium. You know, like the old-fashioned photographers used to use, you know, hold still, flash, and they had a pan with this flash powder in it. That's what it's filled with. So when the picture tube is first manufactured, this thing is sitting in the picture tube like this. They suck all the air out, they seal the end of it, and then using induction, using a coil of wire like an induction stove, which we have in our kitchens at the Golden Tulip. Have you cooked something on it? Oh yeah, you said you cooked fajitas. Yeah, it's pretty cool. Using a coil and induction heating, they hold the coil up to the end of this thing, and it heats this up and flashes, and it burns up all the oxygen that's left in the picture tube. It gets the oxygen out, hence they call it a getter, because it gets the oxygen. So it's just a one-shot deal. It operates when they first manufacture the picture tube. After that, the flash powder is used up, and it just sits there. But this has another function, and that is that this is touching the inside of the glass of the picture tube. When this is inserted in the neck of the picture tube, this pan here, the bottom of it, touches the inside of the picture tube. Well, the picture tube itself is coated with conductive paint. On the outside of the picture tube, there's this gray, let me focus it here. This gray paint that you see, here's where the paint is not, here's where the paint is. And it's all over the outside of the picture tube, and it is grounded. You will always see a ground strap. There's the CRT ground, super important thing, CRT ground. So sometimes it's just some spring-loaded fingers made of brass that touch it. In this case, in most cases, it's spring. It has spring tension on it. It keeps this very, very tight, and it is touching this conductive graphite layer. It's graphite on the outside, and that stuff is called aquadag. That black, grayish black coating that I just showed you there, that coats the outside of the picture tube, is called aquadag. AQUADAG. It is applied wet, hence the name aqua. It is it's a slurry. It's what's known as a colloidal slurry, for what that's worth. It's graphite just mixed with water, and they spray it on the outside of the picture tube, let it dry, and now we have this conductive coating on the outside of the picture tube. There is aquadag on the inside of the picture tube as well. There's aquadag on the inside, and the aquadag on the inside is not connected to the aquadag on the outside. The aquadag on the inside is connected to, let's make sure we're doing this right here. The aquadag on the inside is connected to what we refer to as the second anode. Underneath this guy right here is a connection known as the second anode. There is a first anode. We don't really call it the first anode, but the first anode's kind of like the screen grid. But it isn't called the first anode. This thing is known as the second anode right here, and as you know, there's some kind of high voltage somewhere on that. So it's nothing to be afraid of. I'm quite certain that this is discharged now. I really wouldn't hesitate to stick my finger right in that and pull that off without even doing anything else. I will demonstrate the discharge technique to you now. I'm sure you've done it a zillion times, but this is what I do. And this is like the number one thing that the game collectors are all wigged out about on the internet. And it's like, what's really crazy about the paranoia involved in discharging the second anode is that people will discharge a second anode of the picture tube before they even pull a monitor out of a game. Well, that's ridiculous. I mean, they're up there reaching inside the cabinet trying to discharge a second anode, when if they just unbolted the monitor and took it out, it would be perfectly okay. So I'll just show you this, but I'm sure you've seen it. So the idea when you're discharging a picture tube, it's the picture tube itself that stores the charge. It is not the high voltage unit or anything else that stores the charge. It's the picture tube itself. It stores the charge because the CRT itself acts like a capacitor. And I mentioned this to you the first day of the class. I said, hey, what makes a capacitor is two things that can conduct electricity, and they're really close to each other, but they're not touching and separated by a piece of glass, and that's what we have here. There's aquedag on the outside of the glass, there's aquedag on the inside of the glass, and there's the glass dielectric between them, so we've made our own Leyden jar. Remember, we talked about that before, that this was invented right down the street here in Leyden at the university. So all I need is some sort of a clip lead and some kind of a screwdriver with an insulated handle. You are not grounding the CRT to ground. You are simply shorting the inside of the CRT to the outside of the CRT. So the outside of the CRT, as you know, is grounded. We just talked about that. This is the CRT ground. So the first thing I want to do is connect to that. Now, I can connect to that just by doing this and just by connecting to the frame. But honestly, I would really rather connect to something that I'm pretty sure I'm not gonna lose the connection there. So, I mean, if I clip to the wire there, you know, I can pull on this and it's not gonna come off. On the other hand, if I clip it here and it falls off and it's hanging down here by my huevos when this thing is going into the second anode, that might be a problem, right? So that was my funny joke. I guess they don't know what huevos are here, right? Anyway, so I'm going to connect this guy up to the actual spring itself here, and just here we'll do a POV shot. Let's see if we can do this. POV shot. Ooh, yes, we can. Ooh, here we go.
Nice meeting you.
And I don't expect to hear any sound or discharge. Nah, of course not. You know, because it's self-discharging. All these modern monitors are self-discharging. So I really wouldn't have hesitated to just pull this thing off. And again, it's not this is not where the charge is. The charge is in the CRT itself. Now, as you may know, on some monitors, they are not self-discharging. So I'm going to trick this thing into being a non-self-discharging monitor. What I've just done here is something you should never, ever, ever do, of course, and that is that I'm relying on the suction cup action to hold this in place. It's not actually in there. And it's not really a suction cup. It's not a suction cup to suck the thing on there. It's a boot. It's an insulating boot. It's not meant to hold the thing on there. As you know, there are two little fingers on the end of this thing, and that's what you put inside the second anode hole, which is this guy right here. So I'm going to trick it into being non-self-discharging, and I'm really hoping like heck I don't destroy this monitor. I think I won't. And I'm just going to plug it in until I hear it come on, and then I'm going to turn it off. I hope this works.
Should we use resistor?
Sorry, go ahead.
Is it okay to use screwdriver, or we should use resistor to discharge?
Oh no, just use a screwdriver. There's no reason to use a resistor. You might use a resistor you might use a resistor to discharge a capacitor, but I don't. I just short across the thing. They say you're not supposed to do that. I've been doing it for years. I don't think I've caused a problem. Okay, so as you know, some monitors are not self-discharging. The really old, I think the MTC 900 is not self-discharging. I can't recall exactly. So let's just see if this has retained a charge. What I did was trick it into being non-self-discharging. Let's just see if I get another little spark out of this thing here. No, I didn't charge it up. That's okay. But you know, there's nothing much. There's nothing much to that. Anyway, so connecting to the second anode here. That's called the second anode. Is this really thick red wire, and the red wire goes into the high voltage unit, the LOP-T, the flyback transformer, whatever you want to call it. So the flyback transformer, as you know, creates really high voltage. It's direct current, and it really depends on the size of the CRT. It's about 1200 volts for every diagonal inch of the monitor. So this is probably, what, a 32-inch monitor or something. This could be 35,000 volts, 35 kilovolts or so. And it is DC, and it is positive. Again, it depends on the physical size of the picture tube. The bigger the picture tube is, the higher that high voltage will be. Well, remember I said that painted on the inside of the picture tube is this aquadag. There's aquadag on the outside that's grounded, but the aquadag on the inside of the CRT is connected to that second anode hole. It's not a hole going in, of course, because then you'd let the air in the picture tube. Or as one student tried to convince me, you'd let the vacuum out. You know, why is it sealed up? Oh, is that so we don't let the vacuum out? Yeah, gotcha. So that's all charged at plus 35,000 volts. Okay? So here's the way it actually works. The electron guns themselves just release a cloud of electrons. Remember, they're heated by the 6.3 volt little heater that resides inside the cathode. Heat that up, the electrons come off. Well, I'd like you to think about this for just a second. Let's just say, for the sake of discussion, that the voltage on the cathode was, let's say, plus 130 volts DC. If the voltage on grid number 2 was exactly the same voltage, plus 130 volts DC, would those electrons move anywhere? No, they would not. If I have, remember, voltage is pressure, right? So if I have 150 volts of pressure pushing this way on the electrons, and 150 volts of pressure pushing the other way on the electrons, they're just going to sit there and they're not going to move. Let's increase grid 2. Let's increase G2. As we increase the voltage on the grid, let's say we make it plus 200 volts, now I have more of an attractive force of pulling the electrons this way. Remember that opposite charges attract each other, and the electrons are little negatively charged gizmos, so I'm going to pull them this way, and the higher the voltage is on the grid, the faster they're going to move. Does that make sense to everybody? That's attracting them toward the front of the screen. So we adjust grid G2 to kind of get them moving. Well, they're kind of all in a beam or a ray, as they called it originally, a ray, cathode ray tube, but they're in kind of a beam, but it's not very well defined, so it needs to be focused. So the next thing it goes through, again, is these hollow cylinders. That is the focus grid. So the electrons pass through the focus grid. They're still not going really very super fast. But then all of a sudden they see the accelerator grid. Well, remember that the getter thing is touching the aquadag on the inside, the getter, this guy right here. It's touching the aquadag on the inside. So all of a sudden, these negatively charged electrons are seeing plus 35,000 volts. That's really going to attract the heck out of them. So they shoot toward the accelerator grid, but the accelerator grid has 3 holes in it. So they don't hit the accelerator grid, they go through the opening, which we refer to as the virtual aperture. The aperture, the opening, the aperture. It's called a virtual aperture because we can open and close it depending on the charges that we use on the gun. So they're attracted toward the accelerator grid, which is charged at 35,000 volts, and they are just going so fast now they have a tremendous amount of inertia. Remember, an electron is an itty-bitty thing, but it's not massless. And if it's moving at really close, it's not really exactly the speed of light, but if it's moving really, really fast, it's going to have a lot of inertia. So once it's picked up by the accelerator grid, now it is a gun, and now it's shooting out. And the electron beam, if you will, shoots out toward the front of the screen until it hits the front of the screen like that. And you know, they're really going fast. Here, watch it. See how fast they're moving? Ooh, they're moving really fast. They're going really, really fast. Okay? Then the electrons strike the front of the screen. Coating the inside of the glass front of the screen, there's a substance known as phosphor. Coating the inside of the glass front of the screen, there's a substance known as phosphor. P-H-O-S-P-H-O-R. And there are 3 different colors of phosphor. 3 different types of phosphor, well, 3 different phosphors that glow a different color when they're struck by the electron gun. And typically in the monitors we use, they're laid down in stripes, kind of down the front of the screen. I'll probably be able to show you that later on. So there's like a stripe of red color phosphor, and then right next to that, there's a stripe of green color phosphor, and then right next to that, there's a stripe of blue color phosphor. And of course, you know, those are the 3 primary colors of light, naturally. And they're of course much more closely spaced than I'm showing you here. I'm not gonna do this again here. Just red, green, blue, like that. So these phosphors are phosphorescent. That is to say, when we hit it with a little energy, in this case, the energy is a speeding bullet, an electron, it boosts the electrons in that substance and that phosphor to a higher outer shell. Then when it falls back, it emits a photon of light of one particular wavelength, whether it's red, green, or blue. So what is happening here is these electrons are really moving fast. They strike the phosphor coating the front of the screen, and that's what makes the phosphor glow red, green, or blue, depending on which phosphor it hits. One of the really amazing things about the way the CRT works is that right behind the glass, there's a thing called a shadow mask. Let me just find a picture of it on the internet because it's real interesting. It's a screen that you can kind of hold up and see right through it, and let me write it on the board. There's a hole in the shadow mask that corresponds to each single phosphor dot or line. Right behind here is the screen. I'll show it to you in just a second, called the shadow mask. If you've never broken apart a CRT, you wouldn't know it was there. Let me just find it. Hang on. So this is the shadow mask, and it's a screen that you could, if you picked it up and looked through it, you can see right through it. It's oh, sorry, Chris. This is the shadow mask. So you know, it looks opaque to you in this photograph, but it's really full of little holes. It's like a window screen. It's like a window screen that you know it's there, but you can see right through it. So the shadow mask makes sure that each color hits exactly each electron beam. I'm sorry, red, green, or blue hits exactly. You're throwing up your hands. Did you lose the feed or something?
Yes.
Oh,
It is
we're
automatically-
going to take a break momentarily, and we might push some things around so that it hits the right color. Anyway, so what's really happening here is a transfer of energy. I think you all know that there's a law of physics called conservation of energy that states that you can't destroy energy. It can only be changed from one form to another. If you remember when Spock gets caught on the ice planet and he has to use his phaser to heat up, never mind. So anyway, so what's happening is that these have a tremendous amount of kinetic energy. Kinetic energy is the energy of motion. So these electrons are speeding along. They have a lot of kinetic energy. When they strike the phosphor coating on the inside of the glass front of the picture tube, they exchange that kinetic energy for light energy. Right? So now they're out of energy. Now they bounce off. The electrons bounce off inside. They can't come out the front. The front's made of glass, and glass is an insulator, and no electrons can come out the glass. If it did, you'd probably sterilize all your customers. You probably wouldn't want to do that, or I don't know. You may sterilize your customers. I don't know your customers, but that isn't what happens. It would emit X-rays. It would be a terrible thing. So they really do bounce off inside. However, we cannot allow the electrons to remain inside the picture tube. If we did, they would form a big negatively charged cloud down here in what we call the bell of the tube, the big part. We'd have this big negatively charged cloud. Well, remember, opposite charges attract, but like charges repel each other. You know, this is the same as it is with magnets. With magnets, if I have a north pole and a south pole together, the opposite poles attract each other. But if I have two of the same pole of a magnet, they repel each other. So it's the same thing here. Well, we can't allow those electrons to stay inside the picture tube because we'd have a big negatively charged cloud. And as our electron beam is trying to shoot out of here, it's going to be repelled by this cloud. And unless the electrons can whack against the front of the screen really fast, we won't see any brightness on the screen. So we have to get rid of those electrons, and this is what the high voltage is for. The high voltage at the second anode is not there to attract the electrons toward the front of the screen. That's the job of the electron gun. It's shooting out the electrons. The purpose of the high voltage is to remove the electrons after they've bounced off, and we have to suck them out. So it's like, I'm an electron. Okay, I'm shooting out of my electron gun. I'm shooting out really fast. I strike the front of the screen. Bam! I bounce off. Well, if I'm a little negatively charged electron, I'm going to find plus 35 kilovolts kind of attractive, right? Opposite charges attract each other. So after it bounces off the front of the screen, it finds its way to the nearest outside wall, where it gets sucked out the second anode and into the high voltage unit and past the ground, and that's how we get rid of those electrons. It is a common misconception that the high voltage in a CRT is there to attract the electrons toward the front of the screen, but that's not true, and I can prove that just with a thought experiment here. Here's the aquadag on the inside, and it's connected to the accelerator grid, the last grid right here. There is no potential difference, no difference in voltage between here and here. If the voltage is exactly the same, why would you think it's being attracted toward it? Are you with me on that? Here we had a difference in voltage. It attracted the electrons toward the front of the screen. But over here, the voltage between where it's leaving the accelerator grid and the aquadag on the inside is the same 35,000 volts. So it isn't until the thing bounces off and it's lost its energy that it finds its way out the second anode and into the high voltage unit. Does that make sense to everybody?
Yeah.
So what this means is that if you lose high voltage for some reason, you will have no picture at all in the front of the screen. It'll just be black on the front of the screen. On the other hand, if you see any kind of normal brightness on the front of the screen, you must have high voltage, because if I didn't have high voltage, I wouldn't see anything at all on the screen. And it's been my personal experience that a high voltage is a go, no-go situation. You either have it and it's correct, or you don't have it at all. In every case where we had a problem with low high voltage, right, which sounds stupid, low EHT. We also refer to the high voltage there as EHT, as you probably know, extremely high tension. Another term for voltage is tension. Oh, I forget where I was going.
But Randy, it
Sorry.
looks like that the high voltage red wire,
Yeah.
the suction thing,
Yeah.
sucks out the electrons before they reach the
Ah, this is a great question. Here's his question. To rephrase his question, his question is, well, wait a minute. If the whole inside of the picture tube is charged at 35,000 volts positive, why don't the electrons do this? Boop, boop, and go right to the sides, right? That's your question. And it's a good question. So there's two reasons why it doesn't. Number one, the field is equal around all the sides. I mean, except for the fact that the picture tube is wider than it is tall, the electron feels the same pull to the sides as it does to the top and the bottom. So there's no reason for it to diverge. But that's not the real reason. The real reason is inertia. Again, these are tiny little electrons, but they have mass. And they're traveling, not at the speed of light, but they're traveling really super fast. It takes a tremendous amount of pull to pull them to one side or another. And in fact, I think I can demonstrate this for you. Let me see if I can. Let me see. Okay, so here's an experiment that I'd like you to all do, and then we're going to take a break. His question is, why doesn't it diverge to the side? And my answer is, they have a lot of inertia. They're moving real fast, and it's hard to move them to one side or another. And in fact, it's so hard that we have this magnetic system, which you know is called the deflection yoke. This series of electromagnets that are on the neck of the picture tube. So what I'd like you to do at this break is I have these little magnets here. Grab one of the magnets and hold it near the deflection yoke. You won't get a shock. And you will feel it moving. You'll feel it vibrating your finger. Well, imagine how much more massive your finger is than an electron. So you can feel it moving. So try that when you come up here. Let's take a break and just come up here and grab a magnet. And as I just showed you, just hold it near the deflection yoke and you can feel it moving. Let's take a break and then we'll try to figure out some way to move this stuff around.